What if the biggest questions about non-human intelligence aren't really about if they exist anymore, but maybe why they might be here?
Right. And maybe even more pressingly, why we struggle so much, profoundly to even begin understanding their technology, despite all our efforts.
Exactly. We're talking about some really astonishing recent revelations, things that kind of force us to reconsider, well, everything we thought we knew about our place in the cosmos.
It's a fundamental shift in perspective, potentially.
Okay, so let's unpack this. Today's deep dive is all about non-human intelligence, NHI.
Hmm.
And we're going to explore a really fascinating, maybe unique perspective on why they might be visiting Earth.
And it's not the usual stuff, right? Not conquest or resources.
No, not conquest, not resource extraction, not even just sort of benign observation, maybe. It's something potentially far more profound, something tied intrinsically to their own long-term evolutionary survival.
That's a really interesting angle.
And then we'll pivot. We'll tackle the immense, frankly, mind-bending challenge of how we might ever hope to reverse engineer their technology.
Yeah, that's the other huge piece of this puzzle.
We'll bring in some pretty cutting-edge concepts from, well, the deepest corners of computational complexity theory, stuff that really pushes the boundaries.
It gets very theoretical, but it's grounded in real computational limits.
So our mission today is to try and cut through the noise, sift through all the speculation, and give you the core insights from these pioneering papers by Karim Daghbouche.
These papers really offer a structured way to think about it all.
We're going to help you connect the dots between, say, recent UAP sightings, this heavy-duty theoretical computer science, and the very nature of what it means to be an advanced civilization.
It's about linking observation to some really deep theory.
So prepare to have your understanding of the universe, and maybe our place within it, profoundly expanded, hopefully.
Yeah, the core of our deep dive today, it comes from 3 interconnected papers, all by Karim Daghbouche. And they offer this unique and I'd say scientifically rigorous framework for thinking about NHI.
Okay, so what are we drawing from specifically?
We'll be looking at the bona fide of non-human intelligence, NHI, exploring Earth, evolutionary pressure, and the halting problem. That's the first one.
Got it. Evolutionary pressure, halting problem. Sounds intense.
Then there's computational complexity of UAP reverse engineering.
The how hard is it question.
Exactly. And finally, the genesis of the Fermi Paradox, logical analysis and resolution.
The classic Fermi Paradox.
I
Okay.
mean, the key thing is these aren't just like random thoughts. They represent a formal, evidence-based approach to some of the most profound questions we're facing.
Right. Grounded in logic and observation as much as possible. Okay, so to really set the stage, we need to ground ourselves in what's happening right now in the public sphere.
Yeah, the context is crucial.
The papers we're exploring, they really emphasize that very significant United States House Committee hearing, the one on oversight and accountability. It happened July 26, 2023.
That hearing was a big moment.
Absolutely. This wasn't some, fringe internet forum or a late-night radio show. This was a formal, televised congressional hearing.
Unidentified anomalous phenomena, implications on national security, public safety, and government transparency. That was the title.
Right. And what came out of that hearing was, well, to put it mildly, pretty startling.
Definitely raised a lot of eyebrows.
Because for the first time, really, in such a public and official setting, we had multiple credible individuals testifying under oath about firsthand experiences with UAP manifestations.
And not just sightings, but even claims about potential non-human technology recovery.
Exactly. Imagine the weight of that. You had people like Ryan Graves, highly decorated former Navy pilot. He spoke very compellingly about his own encounters with UAPs, things operating in restricted airspace right off the coast, stuff his squadron saw repeatedly.
And these weren't just blips on a screen. These were objects performing maneuvers that defied known physics.
Then you had David Grush, former intelligence officer, distinguished career.
His testimony was explosive.
Right. He made these extraordinary claims about alleged UAP crash retrieval programs, secret programs spanning decades, and even mentioned the recovery of what he called biological material from non-human sources.
Which is, an incredible claim to make under oath in Congress.
Absolutely incredible. And of course, Commander David Fravor, his famous Tic Tac UAP encounter from back in 2004.
That video is iconic now.
There really is. It's become sort of a cornerstone of this whole public discussion. He recounted his experience in vivid detail: erratic movements, instantaneous acceleration, no visible propulsion.
And the key point here is These aren't just stories anymore. These are formal statements made under the legal penalties of perjury.
Huge personal and professional risk for these individuals.
Massive risk. So the sources we're looking at today define UAP, unidentified anomalous phenomena, quite broadly. It covers the whole spectrum.
So what's the definition they use?
It's airborne objects that are not immediately identifiable, transmedium objects or devices, and submerged objects or devices that are not immediately identifiable and that display behavior or performance characteristics, suggesting that the objects or devices may be related to the objects or devices described.
So air, water, space,
Huh.
and behaving weirdly. Got it.
Pretty much. And as for NHI, non-human intelligence, the definition here is very pragmatic. It's precise.
Right.
It refers to anything non-human able to manifest with documented UAP, i.e. high-tech.
So NHI are the potential operators or creators of these high-tech UAPs.
That's the linkage. So when we talk about NHI today, we're specifically discussing entities associated with advanced technology that is demonstrably not ours, not human origin.
Right, and this forms the new reality, the context for our whole conversation today.
Exactly. And what's truly fascinating here is how these recent revelations, especially that congressional testimony, they directly confront and maybe even resolve one of the most enduring mysteries in science, the Fermi Paradox.
The big one. Where's everybody?
That's the essence of it, attributed to the brilliant physicist Enrico Fermi. It asks a simple but incredibly profound question. If extraterrestrial civilizations exist, and the universe is so mind-bogglingly vast and ancient, why haven't we found any observable evidence of them? Where are they?
It's a question that's haunted scientists and philosophers for decades.
Absolutely. And to really get the paradox, it helps to know a bit about Fermi himself. Enrico Fermi, 1901 to 1954, just a titan of 20th century physics.
Made huge contributions, right? Quantum mechanics, nuclear physics.
Monumental contributions. He was known for his incredible intellect, his ability to solve complex problems almost instantly. Just brilliant.
So how did he get to this paradox?
Well, the crucial context emerged during World War II. His work on the Manhattan Project at Los Alamos.
Oh, the atomic bomb.
Yes. Fermi was instrumental in developing the first self-sustaining nuclear chain reactor, Chicago Pile 1, a fundamental step towards the bomb.
A moment that changed the world.
Completely. And amidst all that intense scientific pressure, the intellectual triumph of harnessing atomic energy, there was also this profound, constant awareness among Fermi and his colleagues. Awareness of the sheer destructive potential of what they were creating.
I can only imagine the weight of that knowledge.
As they wrestled with the implications of that immense power, their conversations naturally drifted. They started asking broader, more existential questions about humanity's future, our place in the universe, the possibility of other civilizations out there.
And whether those civilizations might also discover such destructive power.
Exactly. This deep thinking about humanity's own precarious position, in the face of its own technological might, that really laid the philosophical groundwork for the paradox.
Okay, so the paradox itself.
Yeah.
How does it break down formally?
It really hinges on two key premises that seem to contradict each other. Premise one, the universe is incredibly vast and contains an enormous number of habitable planets.
And we have good evidence for that now, right? Exoplanets.
Abundant empirical support. The Kepler Space Telescope, for instance. Its data suggests there could be at least 100 million potentially habitable planets just in our Milky Way galaxy.
100 million, just in our galaxy.
And then you zoom out. The observable universe, we think maybe 200 billion to 2 trillion galaxies.
That scale is just impossible to grasp.
Right. Each of those galaxies has billions of stars. So statistically, premise one strongly suggests that life, and probably intelligent life, should be pretty common out there.
Okay, so premise one says the universe should be teeming with civilizations. Logically,
Yeah.
statistically.
Exactly, but then you slam right into premise two.
Just
The notable, persistent lack of observable evidence for extraterrestrial civilizations. For decades, we've been listening with radio telescopes, looking for signals, searching for megastructures.
busy city and all that.
Right. And the result seemingly has been silence, the great silence, as it's sometimes called.
So premise one, life should be everywhere. Premise two, we see no evidence of it. That's the contradiction. That's the paradox.
That's the core paradox. The universe should be noisy, full of signals and signs of life. But it appears quiet. At least that was the prevailing view until, well, very recently.
And this is where the UAP evidence comes crashing in.
This is where it gets absolutely critical. If you connect this to the bigger picture, That congressional testimony from July 2023 provides what Daghbouche's papers call strong refutable evidence.
Refutable meaning it could be proven wrong, but it's strong evidence nonetheless.
Exactly. Evidence that NHI may indeed manifest themselves right here on Earth.
Which completely changes the game for the Fermi Paradox.
It's a potential game changer because it directly attacks premise 2.
The lack of evidence premise.
Right. If extraterrestrial civilizations exist and they have the technology to manifest on Earth, which is exactly what the sworn UAP testimony implies, with these descriptions of transmedium craft, incredible accelerations, physics-defying behavior.
Then premise 2, the idea that there's no observable evidence is just flat out invalidated.
Correct. If they are here, being observed, even if not fully understood, then the empirical basis for premise 2 collapses.
So if one of the core premises is fundamentally challenged, undermined by this new wave of evidence,
then the Fermi paradox as a paradox becomes, as the paper puts it, obsolete.
Obsolete because the contradiction disappears.
The contradiction dissolves. It's like, as you said, the paradox of where are my keys vanishing the moment you find them in your pocket. The absence of evidence is no longer a valid observation, so the paradox itself is resolved.
Okay, but there's a nuance here, isn't there?
A crucial nuance. This resolution only eliminates a necessary condition for the paradox, the perceived lack of evidence. It doesn't touch upon the other underlying concerns Fermi had.
Like the potential for self-destruction, the great filter idea.
Exactly. It doesn't imply a sufficient condition to prevent any civilization, including potentially ours, from eventually self-extinguishing. Fermi's original worries, spurred by the atomic bomb, about whether advanced civilizations inevitably destroy themselves, those concerns are still very much on the table.
So even if advanced NHI are visiting us, it doesn't guarantee our long-term survival, or theirs for that matter.
Precisely. The existence of one doesn't negate the risks for all. The paradox simply shifts. It's less, where are they, and more, okay, if they are here, why haven't we fully recognized them before now? What are they doing? And what does their presence mean for our own future?
That's a huge shift in the question. So this compelling UAP evidence suggests a presence, maybe even a visitation. But if they are here, why?
The motivation question.
This is where the papers get really interesting, pushing way beyond those common sci-fi ideas, conquest, resources, even just scientific curiosity.
Right. They propose something much more intricate, something tied directly to the deep nature of advanced evolution itself and the kind of existential challenges even a, utopian civilization might eventually face.
Okay, lay it out for us.
It starts with a fundamental concept, evolutionary pressure, or selective pressure.
Okay, Darwin 101, basically.
At its core, yeah. It's the environmental influences that drive natural selection, the forces that decide which traits, which adaptations, help you survive and reproduce better in your environment.
Survival of the fittest in a nutshell.
Right. And when these pressures are active, individuals or species with the advantageous traits tend to thrive, pass on their genes. The paper also mentions endogenesis.
Endogenesis, what's that?
It refers to evolution or development that originates from within an organism or a system. It's not just reacting to the outside world, but an intrinsic drive for change, adaptation, complexity coming from internal processes.
Okay, internal evolutionary drive. Got it.
Now consider this, and it's a profound hypothetical. What happens when those selective pressures, external and internal, start to diminish? Or even become virtually non-existent.
Like if a species reaches a state of perfect harmony with its environment. Total stability.
Exactly. Imagine an environment so stable, so resource abundant, maybe perfectly engineered by the species itself, that there are basically no external challenges left. No predators, no scarcity, no disease.
Sounds like paradise.
On the surface, maybe? But the long-term consequences, ironically, could be quite negative for that species' viability.
How so?
Well, first, you'd likely see a decreased genetic diversity. Without the constant need to adapt and innovate, the gene pool can homogenize. You lose crucial beneficial traits or just the raw genetic potential for future adaptation if things ever do change.
Right, you lose the toolkit for dealing with the unexpected.
Precisely. Second, reduced adaptability. The population becomes less flexible, less able to respond effectively if new, unforeseen challenges pop up.
They get stuck in their ways, evolutionarily speaking.
Kind of. Which leads to the third point, stagnation or stasis. Populations can become almost frozen in their current state. Minimal evolutionary innovation biologically or maybe even societally.
Things have stopped changing.
Potentially. Fourth, over long timescales, a loss of fitness. Deleterious mutations, things that would normally be weeded out by natural selection, might start to accumulate if there's no pressure against them.
So they become less robust over time.
Possibly. And finally, all this leads to an extreme vulnerability to environmental shifts. If something major and unexpected does happen, a cosmic event, a resource depletion they didn't foresee a population in this state is really poorly equipped to cope. It drastically increases the risk of extinction.
Wow. So it's like evolving yourself into a perfect bubble, but that bubble makes you incredibly fragile if it ever bursts.
That's a great analogy. It seems ideal, this perfect stability, but over the long haul, it's an evolutionary trap. A slow, comfortable slide towards a dead end. Evolutionary atrophy.
Okay, that's a sobering thought. How does this connect to NHI?
This brings us directly to what the paper calls the NDP dilemma. It's a Gedanken experiment, a thought experiment.
Right.
It proposes that these NHIs have achieved ultimate technological mastery through something called non-deterministic processing, or NDP.
NDP. Okay, what on earth is non-deterministic processing?
Okay, imagine a computer. Not like ours that tries one path, then another. Imagine one that can somehow explore all possible computational paths simultaneously, instantly finding the right answer if one exists.
Like infinite parallel processing?
Kind of, but maybe even more fundamental, it's linked to one of the biggest unsolved problems in computer science, P versus NP.
Ah, P vs NP. I've heard of that. Whether problems easy to check or also easy to solve.
Exactly. If P actually equals NP, meaning every problem where we can quickly check a proposed answer, we could also quickly find that answer, it would change everything.
How so?
We're talking cures for all diseases, unlimited clean energy, cracking any encryption, maybe even things like instantaneous interstellar travel, controlling inertia, creating a true post-scarcity zero marginal cost economy. It would be a technological singularity.
Wow.
An NDP system, the paper suggests, would be the embodiment of that PNP power. A technology that can solve problems currently completely intractable for us. And the paper conjectures that mastering NDP might be a necessary condition for any civilization capable of routine interstellar travel and the kind of tech UAPs display.
So the idea is these NHIs are maybe millions, even billions of years ahead of us.
That's the hypothesis. They've journeyed so far technologically and evolutionarily. And through mastering NDP, they've achieved something akin to a utopian existence.
What would that even look like?
Imagine meticulously engineered ecosystems, perfect balance, maybe breathtaking beauty. Disease, non-existent, cured, eliminated. Every individual has instantaneous access to all knowledge, maybe even experiential access.
Like downloading skills matrix style.
Perhaps even deeper than that, a societal fabric woven from pure curiosity, art, science, technology that unlocks the universe's deepest secrets. Maybe even exploring spirituality, consciousness, existence beyond physical form, transcending bodies entirely, potentially.
It's almost impossible to conceive. Cosmic fulfillment.
Right. But here's the twist. Here's where it gets really profound and kind of unsettling.
Right.
In that unbelievably advanced utopian state, all those traditional evolutionary pressures we talked about, scarcity, competition, disease, struggle, they're not just lessened, they're virtually eliminated.
Because they've solved all those problems with NDP.
Exactly. And paradoxically, this leads to a critical halt in their endogenetic evolution. Remember that internal drive for change?
Yeah, evolution from within.
That stalls. They've optimized themselves so perfectly that the very forces driving biological innovation, societal adaptation, creative problem solving, those forces just aren't acting on them anymore.
So they achieved perfection, but perfection leads to stagnation. That's the dilemma.
That's the NDP dilemma. A fascinating, deeply terrifying possibility for any super advanced civilization. They have everything, but maybe at the cost of their intrinsic ability to become something new.
Wow. Okay, so how do they deal with that? Or can they deal with it?
Well, this apparent paradox leads us to another fundamental limit, a real cornerstone of computational theory. The halting problem.
Halting problem. Okay, I've heard of this too. Alan Turing, right?
The very same. It's a classic decision problem. Can you write a program that looks at any other program and its input and tells you for sure, yes or no, will that other program eventually stop, or will it run forever in an infinite loop?
And the answer is?
The answer, proven rigorously by Turing, is no. No such general program can exist. It's fundamentally unsolvable by any algorithm.
Why not? It seems like something a powerful enough computer should be able to figure out.
It boils down to self-reference and contradiction. Imagine you did build that perfect halting detector. Now feed the detector itself as input, but with a twist. Tell it to do the opposite of its own prediction.
Okay.
If the detector predicts it will halt, instruct it to loop forever instead. If it predicts it will loop forever, instruct it to halt immediately.
It creates a paradox. If it halts, it should loop. If it loops, it should halt. It can't logically exist.
Exactly. It's like the liar paradox. This statement is false. If it's true, it must be false. If it's false, it must be true. It breaks logic. Turing showed computationally that any program trying to solve the general halting problem runs into this kind of inescapable contradiction.
So some questions are just inherently undecidable by computers.
Undecidable, not just hard, but impossible to solve algorithmically. It's a fundamental boundary of computation.
Okay, that's a huge concept. Well, what does this computer science problem have to do with NHI evolution?
The insight here is profound. Even these NHIs, masters of NDP living in utopia, they still face this fundamental limit. They cannot, the paper argues, reliably predict the best of evolution for themselves. They can't compute the optimal path for their own future internal endogenetic evolution.
Why not? Because trying to predict their own evolution is like the halting problem.
Precisely. The paper formalizes it with a hypothetical function, let's call it predict optimal evolution, NHI. But when you try to apply this function to the NHI themselves, self-referentially,
It runs into the same contradiction.
it encounters the same inherent undecidability. Trying to forecast and optimize a system that inherently changes its behavior based on those very forecasts, it's a paradox. They're stuck. They've reached a state of potential evolutionary stasis, unable to reliably predict or steer their own biological or societal future through purely internal means or calculations.
That is really fascinating. So they're stuck in paradise, unable to evolve further.
Potentially. But the papers hypothesize something even more remarkable. These NHIs might have foreseen this exact evolutionary dilemma, this halting problem for their own species.
They saw it coming.
Maybe well before they even reached full utopian existence. Think about that level of foresight. Predicting their own evolutionary dead-end centuries, millennia, maybe even eons in advance.
That's almost godlike prescience.
It suggests an incredible depth of understanding about complex systems and computation. So their strategic anticipation was key. They realized that trying to artificially induce struggle or selective pressures within their utopia would be contradictory, right? It would violate the very state they achieved.
Yeah, you can't just start wars or plagues to keep evolution going if you've already eliminated them.
Exactly. So their solution, the hypothesis goes, was to circumvent this internal stagnation by looking outward, by delving into evolutionary narratives on worlds beyond their own.
So instead of trying to fix the problem from inside, they look outside.
They look outside. They aim to study diverse evolutionary solutions across the cosmos, systematically studying these external evolutionary achievements, as the paper puts it.
To learn from others.
To observe, analyze, and maybe distill the best solutions, the most interesting adaptations, the novel evolutionary pathways that other life forms have discovered through their struggles and pressures.
And then integrate that knowledge back into their own framework.
That seems to be the idea. It's a grand analytical expedition, a quest for cosmic evolutionary wisdom. They use their incredible NDP capabilities not to predict their own intractable future, but to mine and analyze the evolutionary wisdom scattered across the stars.
Shifting from self-prediction to cosmic exploration and data mining.
It's a profound strategic shift, from internal computation to external observation and analysis.
So this leads to a completely different understanding of why they might be here, the bona fide of their visits.
Exactly. This hypothesis leads to a powerful conclusion. NHI visits likely transcend those simplistic notions of conquest or exploitation, or even just pure science.
What's about their own survival?
It encompasses a deliberate endeavor aimed at exploring and studying diverse evolutionary solutions, including those present within the human habitat. We, and all life on Earth, represent a unique evolutionary dataset developed under pressures they no longer experience.
So we're interesting case studies for them.
Potentially, yes. Valuable examples of ongoing evolution, adaptation, maybe even societal dynamics born from scarcity and struggle. Things they've moved beyond but perhaps need to understand or reintegrate in some way to avoid permanent stagnation.
The paper even mentions some controversial phenomena in this context, right?
It does. It carefully notes that indications from reported cases of bovine excision, cattle mutilation, alien abduction, and the absence of overt hostility suggest a more nuanced understanding of NHI motivations.
Suggesting these might fit the pattern of data gathering. Biological sampling, maybe?
One rooted, the paper says, in the quest for evolutionary knowledge and survival rather than overt aggression. It presents these unusual, often unsettling reports not as proof, but as potentially consistent with this hypothesis of information gathering for evolutionary purposes, rather than simple malice or conquest.
Okay, that is a huge reframing of the entire UAP discussion. It shifts the focus from threat to something much more complex, almost philosophical.
It certainly offers a different lens.
But this raises the flip side of the coin for us. If NHIs are here, driven by these incredibly deep motivations, can we here on Earth ever hope to understand their technology?
The reverse engineering challenge.
Let's shift gears to that now. The immense, maybe insurmountable difficulty of UAP reverse engineering. First off, maybe just quickly define reverse engineering for us.
Sure. At its heart, reverse engineering is figuring out how something works. Its internal design, its function, its operating principles, just by looking at it from the outside, by observing its behavior, without any blueprints or manuals.
Like taking apart a radio to see how it makes sound, but maybe without even being able to take it apart fully?
Exactly. You're given a black box, essentially. You poke it, you prod it, you observe what it does, and you try to deduce the mechanisms inside.
What are the typical steps?
Usually you start with observation and data collection. What can you see it doing? Then decomposition and abstraction, trying to break it down into functional parts or principles. And finally, reconstruction and validation, trying to build a model, physical or theoretical, that replicates the behavior you observed.
And you mentioned even for normal human-made stuff, this can be hard.
Oh, yeah. Even reverse engineering complex software or hardware made by other humans can be incredibly challenging, computationally intensive, sometimes provably hard, even NP-complete in certain cases.
Okay, so already hard. Now apply that to UAPs.
Right. And Daghbouche's paper takes a fascinating formal approach here. It models UAP reconstruction as an automaton identification problem.
Automaton identification. Okay, what's an automaton in this context?
Think of it as an abstract model of computation, like a finite state machine. It has a limited number of internal states, it receives inputs, it follows rules to transition between states based on those inputs, and it produces outputs.
What's the example in the paper?
The music box. Exactly. That's a great simple illustration. The states are the different rotational positions of the cylinder. The inputs or experiments are the interactions between the pins on the cylinder and the teeth of the comb. The outputs are the musical notes played.
So it has states, inputs, transitions, outputs, a basic model.
Right. Formally a finite set of states, an input alphabet, a state transition function, the rules, an initial state, and an output function or set of accepting states.
But why use such a seemingly simple model for something as complex as a UAP?
Well, several reasons. First, simplification. Even highly complex engineered systems can often be abstracted down to discrete state transitions at some level. It helps manage complexity.
Okay.
Second, modeling input-output. Automata are great at capturing how a system responds to different inputs over time. Third, finite complexity. Even if the real system is vast, focusing on observable behaviors often deals with finite, discrete actions, which fits the automaton model.
And it allows for theoretical analysis.
Crucially, yes. Using automata provides a rigorous mathematical framework to analyze the limits of what we can actually deduce or reconstruct. It lets us talk about computational hardness.
Okay, so how does the paper use this with this matrix thing?
Right. The paper introduces a formal tool, the State Characterization Matrix, MDTE. Let's break that down.
DTE?
D is for data, all the UAP observational information we can possibly gather. And this data falls into two main types, which is important.
Two types of data.
First, operational non-reproducible observations. These are the field sightings, often passive observations, things we can't easily replicate in a lab.
Like the famous 5 observables.
Exactly like those. Positive lift without flight surfaces, flying without wings or rotors, sudden instantaneous acceleration, pulling g-forces that should crush any known craft or pilot, hypersonic velocity without signatures, going incredibly fast without sonic booms or heat trails.
Transmedium travel moving seamlessly between air and water, or even space.
Right. And low observability or cloaking being hard to detect. Plus, sometimes those reported biological effects on humans and animals nearby, these are all part of the D dataset, but they're hard to work with systematically.
Because they're unpredictable one-off observations mostly.
Exactly. The second type of data in D is reproducible analysis data. This is the kind of data you'd hope to get from, say, purported crash retrievals or controlled lab analysis, if such things exist and are accessible.
No, what would that include?
Things like highly structured material characteristics. The paper highlights isotopically engineered materials.
You mentioned this before, materials engineered at the isotope level.
Yeah, imagine designing materials by precisely controlling the number of neutrons in the atoms. Not just the element, but the specific isotope. This could yield extraordinary properties, electromagnetic, mechanical, quantum, totally outside our current material science playbook. It creates a vastly expanded design space.
Making it almost impossible to guess how they made it or what it does.
Immensely intractable. It's like comparing Bronze Age metallurgy to modern nanotechnology, but maybe an even bigger leap. Also in this category would be systemic measurements, precise weight, dimensions, energy calculations, internal layouts derived from any actual physical artifacts.
Okay, so that's D, the data. What about T and E?
T is the set of test states, the theoretical inputs we might apply. The model assumes it's prefix complete, meaning if you consider a sequence of inputs, all its shorter starting sequences are also included. It ensures you consider all intermediate steps.
E.
E is the set of experiments or observed outputs. Assumed suffix complete, meaning if you observe an output sequence, all its ending segments are also considered. This captures the consequences of later parts of input sequences.
So ideally, if you have perfect D, T, and E, you can build the matrix and figure out the automaton.
In a perfect world, yes. If the matrix MDTE has no holes and T and E are complete, the reconstructed automaton should match reality. But with UAPs, our D is patchy, T and E are mostly hypothetical. It's full of holes.
Which brings us to the computational difficulty, NP complete.
Exactly. Now we get to the core computational challenge. The paper references work by E. Mark Gold from 1978, showing that reconstructing even a basic finite automaton from observations is NP complete.
Remind us what NP complete means again. Hard to solve, easy to check.
Basically, yes. Problems where if someone hands you a potential solution, you can verify if it's correct relatively quickly, in polynomial time. But finding that solution yourself might take an exponential amount of time. As the problem gets bigger, it's computationally very hard.
And the P versus NP question is whether these hard-to-find problems can actually be solved quickly. We just don't know how yet.
Right. It's arguably the biggest unsolved problem in computer science and mathematics. $1 million prize for solving it. Most suspect P is not equal to NP, meaning these problems really are fundamentally hard to solve quickly.
Okay, so how do Gold's theorems make UAP reverse engineering NP complete?
Well, Theorem 1, data matrix agreement, says the matrix, MDTE, gives you a valid automaton only if T is prefix complete and E is suffix complete. But our UAP data D is inherently incomplete, fragmented, so the condition often isn't met.
We have holes in the data.
Big holes. Then Theorem 2, transition assignment is NP complete. This is critical. Figuring out the hidden internal state transitions of the UAP based only on the observable inputs and outputs we have, that task is computationally equivalent to solving a Boolean satisfiability problem, SAT.
And SAT is famously NP complete.
The classic NP complete problem. So while checking if a proposed UAP automaton matches the data might be feasible, polynomial time, finding the correct automaton in the first place is computationally intractable. The search space is just too vast.
Okay, that's a huge barrier already. Any other theorems compounding this?
Yes. Theorem 3. Minimal set of test states may not be minimum. Even if we could somehow figure out the test conditions needed, T and E, the set we find might not be the smallest, most efficient one. This further complicates things, potentially expanding the search space again.
Making it even harder to find the simplest explanation.
Right. And Theorem 4, identification in the limit. This basically says that even if you theoretically have enough well-structured data, the amount of data needed to reliably identify the automaton grows exponentially with its complexity. So in practice, it quickly becomes intractable.
So even before we consider the alien aspect, just the pure computational logic of reverse engineering from limited data makes it NP complete incredibly hard for us.
That's the baseline difficulty, yes.
But the paper argues it gets even worse than NP complete, right? It could escalate.
Oh, yes. Here's where it gets truly mind-bending. NP complete is already a massive hurdle. But UAP reverse engineering could be much, much harder, potentially TS base hard, or even undecidable.
Undecidable, like the halting problem. Meaning no algorithm can even tell if a solution exists.
Exactly, that level of difficulty. So why the escalation? Several factors. One huge one is unknown physics.
If they're using physics we don't even know about.
Precisely. If UAPs operate on exotic or unknown physical principles, things totally outside our current scientific understanding, then the system's internal state space isn't just large, it might be effectively unbounded or infinite from our perspective.
We can't even define the limits of what it could be doing.
Right. This lack of theoretical constraint, this inability to bound the problem, can push the difficulty up from NP-complete to PS space hard. That requires polynomial memory, but potentially exponential time even harder. Or, yes, potentially into the realm of undecidability. If the physics is truly alien, maybe no algorithm within our physics can ever model it correctly.
Wow. Okay. Unknown physics is one factor. What else?
The data itself. Severely fragmentary data. We touched on this. Our observations are incomplete, fleeting, uncontrolled. We're trying to reconstruct this hyper-advanced machine from blurry photos and anecdotes, essentially.
Not exactly ideal lab conditions.
Far from it. This forces any reconstruction effort into an exhaustive exponential search just to try and fill in the gaps in that state characterization matrix. The incompleteness itself dramatically ramps up the computational complexity, pushing it towards these higher classes.
We don't have enough pieces, and the missing pieces are almost impossible to guess correctly.
Exactly. But perhaps the most profound hypothesis for why it's so hard is the concept of metacomputer architectures.
Metacomputer, what does that mean?
This goes beyond just materials or propulsion. It speculates about the fundamental nature of the UAP technology itself as a computational system. First, back to those isotopically engineered materials.
Right. Designed at the subatomic level.
The paper suggests these materials aren't just strong or weird, they might be computationally active. Their precisely engineered isotopic structure could create an exponentially vast configuration space, not just for material properties, but for information processing.
So the material itself could be part of the computer.
Potentially, yes. Which leads to the second idea, functioning beyond von Neumann architectures. Our computers mostly have separate memory and processing units, right? Data moves back and forth.
The von Neumann bottleneck.
Right. But imagine a UAP where the material itself intrinsically performs computations. Signal processing, decision-making, happening right within the atomic structure of the material. It acts as a meta-von Neumann computer architecture.
So the structure is the computation.
That's the wild idea. The paper speculates that perhaps every computable function is somehow pre-materialized and can be instantly accessed via the quantum states of the material. The material is the computer in a way we can barely conceive.
It's hard to wrap my head around.
It leads to a stark comparative complexity. Our best current models, supercomputers, even quantum computers, would be, as the paper puts it, rudimentary as medieval automata compared to such a system. Our whole way of thinking about computation might be inadequate.
Which brings us back to that fantastic analogy the paper uses.
The smartphone in the hands of Neanderthals.
Let's break that down again because it's powerful.
Okay. So a Neanderthal finds a smartphone. They might recognize it's weird, artificial, maybe they can make the screen light up, make a noise. They observe some output.
But they have no concept of what's inside.
None. The integrated circuits, the software, the operating system, the communication protocols, it's all completely alien. The concepts themselves are beyond their understanding.
And crucially, the stuff that makes it work.
The supporting infrastructure. The internet, the cell towers, the Wi-Fi, the satellites, the fiber optics, the data centers. All that invisible network is entirely beyond Stone Age understanding. They can't even conceive of it.
That's the suggested gap between us and UAP tech. Not just a difference in degree, but a difference in kind. Maybe multiple kinds.
That's the implication. The gap might be that vast, spanning physics, materials science, computation, maybe even dimensions.
So given this level of intractability, this potential undecidability, what does the paper say about current efforts? Like governments trying to figure this stuff out?
It argues that efforts to classify UAP technology for, say, technological supremacy are fundamentally absurd.
Absurd. Strong word.
Because if you can't even begin to understand the fundamental principles, let alone replicate them, how can you classify it for military advantage? It's like trying to classify alien biology based on seeing a shadow.
And what about, say, private investment, venture capital chasing UAP tech?
Similarly, the paper concludes that venture funds, or R&D targeting frontier tech related to UAPs, would face an insurmountable reverse engineering challenge with contemporary methods.
Basically, don't waste your money trying to build a UAP based on current science.
That seems to be the takeaway. The fundamental computational limits, NP completeness, potential undecidability, the halting problem lurking in the background, prevent meaningful progress using our current tools, our current scientific and computational paradigms. We're just not equipped.
This raises a really daunting question then. If we can't reverse engineer it with current methods, if it's fundamentally beyond our grasp right now, is there any path forward, or are we just stuck?
Well, this is where the whole argument circles back, fascinatingly, to non-deterministic processing, NDP.
The very technology the NHIs are supposed to have mastered, the
Yeah.
one causing their stagnation potentially.
Exactly. The paper posits that NDP techniques, if they could be developed, have the potential to reduce NP-complete problems to polynomial time complexity.
Meaning NDP could solve these problems that are intractable for us, make them feasible.
Theoretically, yes. It could potentially crack NP-complete problems, making them solvable in a reasonable amount of time. And this is crucial because, as we've laid out, classical reverse engineering efforts remain fundamentally doomed by their inability to manage exponential complexity and incomplete data. Our current way of computing just hits a wall.
So NDP isn't just the NHI's potential problem, it's also the potential solution for us understanding them.
It's presented as the key, the transformative key. It suggests that our entire current approach, our scientific method based on classical computation, might be insufficient when facing something truly deeply alien.
We need a new way to think, a new way to compute.
Precisely. And most importantly, the paper argues NDP provides the critical framework to fill in the holes in that state characterization matrix. Remember all the missing data?
Yeah, the fragmentary observations.
NDP, hypothetically, could work differently. It could perhaps integrate new mathematical and physical frameworks to systematically address the gaps and uncertainties inherent in fragmentary observational data?
How? By exploring all possibilities at once.
Perhaps. Or maybe by operating on principles that allow for logical inference and reconstruction, even from sparse data, in ways our current algorithms can't. It's not just about being faster, it's about a fundamentally different way of processing information, maybe even redefining what information is and how it relates to physical reality.
Wow, so it's a conceptual leap, not just building a faster computer.
A fundamental paradigm shift, which leads to the paper's conclusion on this. Only a transformative approach based on NDP can yield efficient and reliable reconstructions of UAP systems.
So forget better conventional methods. We need a revolution in computation itself.
That's the implication. To truly understand their technology, we might first need to achieve something akin to their apparent level of computational mastery. We might need to figure out if P&P understand the implications and then build technology based on that foundation.
That's a goal that challenges the absolute boundaries of our scientific ambition. It's almost unimaginable.
It certainly sets the bar extremely high.
Okay, let's try and unpack all of that. We've covered a lot of ground here, taken a deep dive into some truly mind-bending stuff.
Definitely some heavy concepts.
We explored this revolutionary idea about why NHI might be visiting. Not as conquerors, maybe not even as scientists in our sense, but perhaps as these incredibly advanced explorers.
Explorers looking for solutions to their own almost unimaginable problem, evolutionary stagnation.
Right, a stagnation ironically brought on by achieving a technological utopia, potentially through mastering NDP, and tied into the deep limits of computation, like the halting problem.
They can't compute their own best future, so they look outward.
And then we saw why understanding their tech, reverse engineering UAPs, is such an unbelievable challenge for us.
Rooted in computational complexity, NP completeness, maybe even undecidability.
Driven by unknown physics, fragmentary data, and these wild possibilities of metacomputer architectures, isotopic materials. The smartphone for Neanderthals gap.
It paints a picture of visitors whose motives are incredibly complex, maybe existential for them, and whose technology is just operating in a different reality from ours.
So this whole deep dive, it raises a really important final thought, doesn't it?
I think it does. Regardless of how sophisticated evolution gets, whether it's purely biological or technologically augmented like the hypothesized NHI, maybe we need to recognize that all evolutionary solutions, no matter how advanced, are ultimately transient and alternative adaptations within the vast tapestry of creation.
Nothing is permanent, not even a technological utopia.
That seems to be a potential implication. Nothing is truly static or final in this incredibly dynamic universe. That drive to adapt, to change, to find new solutions, maybe that's a fundamental, inescapable part of existence itself at every level.
Which makes you think about us. As we push our own computational advancements forward, develop AI, pursue our own technological progress, could we, paradoxically, be heading towards our own kind of stagnation?
It's a provocative question the paper implicitly raises. Could our own optimization, our drive to solve problems and eliminate pressures, eventually lead us into a similar trap, just like the one hypothesized for NHI?
Are we maybe engineering away the very challenges that make us resilient, adaptable, creative?
It invites us to really contemplate that delicate balance. The balance between advancing our amazing technological capabilities while somehow preserving that natural impetus, that internal drive for evolutionary diversity and adaptability, not just for hypothetical aliens, but for humanity itself.
It's a profound reminder, isn't it? That true progress might not just be about faster chips or more powerful AI, but about maintaining the underlying conditions for adaptation, for change, for continued evolution in its broadest sense.
Maybe the biggest lesson from even contemplating these profound others is actually a lesson about ourselves, about our own journey, and making sure we don't inadvertently engineer ourselves into an unforeseen evolutionary corner.
Wow. Well, we hope this deep dive has given you, our listener, a whole new framework for thinking about intelligence, technology, evolution, and really our place in this vast, mysterious universe.
Hopefully sparking some new connections and questions.
Keep seeking out those surprising facts, keep connecting those dots, even the ones that seem wildly far apart, and definitely keep asking those big, universe-shaping questions.